let's get started. And I was gonna say, can you see my screen? But I realized that we are offline. Yeah. But anyway, yeah, thank you very much for coming to my talk. This is a gentle introduction to scaling up machine learning service with Kubernetes and Mlflow. I'm happy to see all of you in the audience. I guess using lots of buzzwords in the title worked well. Right. So before we begin, it's going to be mainly about the introduction to Kubernetes service deployment. So I expect you to know the Docker basics of Docker. So, yep. So let me quickly introduce myself. My name is Kei Nemoto. I'm a data scientist at the Montefiore Einstein Center for Health Data Innovations. In my work, I mostly do ML ops type stuff. I build CI/CD pipelines, ETL pipelines. In my previous organization, I was developing the backend, and I was developing NLP models a lot. This is my LinkedIn account. I'm happy to get connected with you all. And this is my GitHub account. And I'm going to show some code for this talk. And all code is available on my GitHub, so please check out. OK, so let's get started. So let's imagine that you're working as a machine learning engineer. And one of the data scientists in your team developed a random forest model for, like, let's say, iris prediction. And you are asked to deploy the machine learning model as a microservice. So this is our tech stack would look like. So the random forest is implemented in scikit-learn. And we're going to use Flask to create a REST endpoint. And we're going to use gUnicorn as a WSGI HTTP server. And we're going to package everything into Docker containers. So this is just the example code for the Flask service. I hope nothing new here. So the model is random forest classifier. And we implement post method in Flask. And it receives request as a JSON. We pass the JSON input into model.predict. Model generates prediction. And we generate a response, including a prediction, and returns the response as a JSON string. So, so if we visualize the deployment strategy for this model, it would look like this. And let's call this single container deployment. So first, we have a host VM. And on the host node, we have a Docker container running. And within the Docker container, there's gUnicorn server running, and the Flask service running, and so on. And there should be a bridge between the Docker's specific port and the host VM's port. So the connection is established. And client can send a HTTP request to the host VM's specific port. And as soon as the request hits the node, it's going to be forwarded to the gUnicorn. gUnicorn sends the request to the Flask service. Flask service is going to generate a response using the scikit-learn model and sends the response back to the client. So this is similar to what I did in the past in my work. I was happy I finished my task. I went home, cooked dinner, went to my bed, and this happened. So let's review like what went wrong with single container deployment. What are the problems? So the first problem is straightforward. If the host VM goes down, your service goes down. And VMs fail for many reasons, and I learned my lesson in a very bad way. And what about update downtime? While you're upgrading your service from V1 to V2, you have to switch your container from V1 to V2. So there is going to be a update downtime. And this means that your service is not highly available, which is not a great thing for the production service. And what about scalability? The resources of the container are bound to the resources of the host node. So your Docker container cannot be bigger than the host node. So it's going to be a scalability issue. And to solve these problems, sorry, yeah. This means that single container deployment has an issue with scalability and high availability. And we want the production system to be highly available and scalable. To achieve that, we can use Kubernetes. So what is Kubernetes? Kubernetes is a container management system. So let's think about the life cycle of the containerized application. So the life cycle consists of these 4 stages. The first stage is the building. You build image. And the second stage is the deployment. You deploy your image into some image repository. And the next stage is scheduling. And scheduling means you decide when and where to run your container. Once your container is running, the last stage is going to be the management of the container. Management involves deletion of the container, upgrading of the container, and so on. And it turns out that Docker is a great tool to cover the first 2 steps in this life cycle, but it doesn't natively support the last 2 stages in this life cycle. And you can use Kubernetes to natively support the last 2 stages. So I want to emphasize that Kubernetes is not a replacement of Docker. Rather, by using them together, you can fully support this full container lifecycle. And when we think about the relationship between Docker and Kubernetes, there is awesome documentary on Kubernetes created by Honeypot on YouTube. I highly recommend you to watch this documentary. It's really good. And an interviewer asked an interviewee, so what is Docker and Kubernetes anyway? And the interviewee's response is that, so let's imagine we invent the post office. Docker creates an envelope. Envelope is a container. And Kubernetes is the postal system that delivers envelopes to the destination or the VMs. So now we understand the relationship between Docker and Kubernetes. Let's move on to the Kubernetes 101. So this gray area is the Kubernetes cluster. A Kubernetes cluster consists of the control plane and the workers. Control plane is the brain of the Kubernetes. It has a scheduler for the scheduling, a controller manager for the maintenance of the container, and the etcd is like the database of the Kubernetes. So it's kind of the memory of this brain. And we have an API server talking to the workers. And control plane can be run on a single VM or multiple VMs. And we have workers. On each worker, we have a component called a kubelet. Kubelet is kind of the agent of each worker. And it's going to talk to the API server, receives the request from the API server, processes the request. And worker is just a single VM. So each VM can be one VM can be one worker. And you see pods in this diagram. So pod is a Kubernetes component that executes the containers. That's all what it does. And it's very unique in Kubernetes that each pod gets its own unique IP address. So as long as you're in the Kubernetes cluster space, you can talk to pods by using their IP address. So let's go back to the problems we reviewed. How can we build a scalable and highly available service on using containers? So the Kubernetes answer is called deployment. A deployment consists of a set of replicas of the same container from the same image. So let's take a look at an example. We have pod A, B, C, and D running on this cluster. So these pods are identical replicas of the same container. Let's say our machine learning service image. So let's think about how can this how this architecture can solve the issues we had. So scalability is very straightforward in this architecture. Since pods are just identical replicas, they're going to generate the same response for the same request. So we can just distribute, requests across pods. And you can add more workers to this cluster so you can horizontally scale out your service. What about high availability? Let's say node 1 went down. That means the pods running on the node 1 go down as well. And but it's not a problem because we have identical replicas in node 2. So when the client sends a request, we can forward the request to the node 2 pods running on the node 2. While we recover node 1, maybe we can add a new node and create run a pod. What about update? Kubernetes natively supports rolling update. So this is how it works. So while you upgrade some pods to version 2, you still keep some pods alive. So when the client sends a request, the request goes to V1 pods. And once V2 pods are ready, you can send a request to the V2 pods. And you can update, while you do that, you can update the rest of the V1 pods. So it's not going to be any downtime for the update. So this is a configuration file for deployment. In Kubernetes, you can write a YAML file to create Kubernetes components. So let's take a look at line 2. At line 2, you specify the kind. Kind means what kind of components you want the Kubernetes to create, and which is deployment in this case. From line 3 to line 7, we can specify the metadata, meta information about this deployment. At line 9, you specify the number of replicas for this deployment. And at line 20, you specify the image associated with this deployment. And at line 22, you specify the port for this service. By the way, this configuration file is available on my GitHub repo, so please check it out later. And once you create a YAML file, you can pass the YAML file to the kubectl apply. Kubectl apply is going to talk to the control plane to process your request. So, and you can check the pods information using kubectl get pods. So this is what your deployment looks like. As you can see, there are 3 pods running for this deployment. And each pod gets its own unique IP address, and they are coming from the same image. Okay, and as I said, as long as the client is in the Kubernetes space, they can send a HTTP request to specific pod using pod's IP address. So this is great, but the question becomes, how can we decide which pod to send a request to, since they're just identical replicas of the same container? And the Kubernetes answer is called cluster IP service. Cluster IP service creates an endpoint for deployment, not for the pods, but for the deployment. In this, and the cluster IP works as a load balancer that distributes traffic across pods. So in this manner, the client can send the HTTP request to the cluster IP, and cluster IP it's gonna decide which pod to forward this request to. In this example, cluster IP decided to use pod C. So pod C is gonna receive the request and processes the request, generates a response, and sends the response back to the cluster IP, and cluster IP forwards the response back to the client. So this is how you can create a cluster IP service. I put the configuration for the deployment to emphasize that you need a deployment to create a service. But this configuration is the same as the configuration I showed you before. So let's take a look at the diagram on the right-hand side. So this is a configuration for the cluster IP service. At line 38, you specify the kind, which is service. And from line 44 to 46, you specify the port for this service and the cluster IP. And at 48, you specify the deployment associated with this cluster IP service. And at the end of this configuration, you specify the type of this service, which is cluster IP. And this is what the cluster IP looks like. You can get service information by using kubectl get services. And as you can see, cluster IP gets its own unique IP address, and it's listening at port 5000. Okay, so this is great, but this gives us a question. Let's say we have a legacy system which cannot be run on Kubernetes, but the legacy system wants to use our machine learning service. So the question becomes, how can we expose our machine learning service to outside of Kubernetes? And the Kubernetes answer is called node port. Node port exposes a specific port on all the workers, and it's going to expose the same port on every worker in this cluster. And in this manner, the client can send a HTTP request to any of the workers at specific node port. And as soon as the request hits the node port, it's going to be forwarded to the cluster IP, and cluster IP does the rest of the routing. So this is configuration for the node port. The only difference between configuration for the cluster IP and the configuration for the node port is the last line. The kind is still service, but instead of saying type is cluster IP, you say type is node port. And you can, as you can see, there is node port running. And as I said, node port creates cluster IP and exposes a specific port. In this case, it decided to expose port 31304. So this is great. Services outside of Kubernetes can talk to our machine learning service. But this gives us a question. How can we decide which node to send a request to? And the Kubernetes answer is called load balancer. Load balancer service creates a load balancer instance outside of Kubernetes. And the load balancer distributes traffic across nodes. So there is a distinction between cluster IP's load balancing and the load balancer's load balancing, because cluster IP is a load balancer for the pods. But load balancer service is a load balancer for the nodes. In this manner, the client can just send a HTTP request to the load balancer, and it's going to figure out the rest of the routing. And as soon as the request hits any of the workers' specific node port, it's going to be forwarded to the cluster IP, and cluster IP does the rest of the routing. So this is a configuration for the load balancer service. Again, the only difference between other services configuration is the last line. You specified that the type is load balancer. Usually, you run a load balancer service on a cloud provider, on any cloud provider, such as ALB by the AWS. But there are some on-prem options for the on-prem load balancer. Okay, great. So our service is fully exposed, can be accessed inside and outside of Kubernetes cluster. But this gives us a question. Since we are only getting one request, should we run all the 4 pods? Aren't we wasting resources? And the Kubernetes community's answer is called Knative. Knative is a third-party Kubernetes extension that allows you to create a serverless service. And the Knative exposes itself outside of Kubernetes. So it's going to create an endpoint accessible from outside of Kubernetes. And the definition of serverless can vary, can have multiple meanings. In this case, serverless means that there is no pod running when there is no request coming. And we run the pods based on the number of requests. So let's take a look at an example. So let's say the client sends a request to the Knative instance. Knative is going to check whether any pods associated with this Knative service running. If there is no pod running, it's going to ask the API server to create a new pod. API server is going to say, no problem. It's going to talk to the kubelet, and kubelet is going to create a pod. And as soon as pod is available, Knative is going to forward the request to the pod, and pod is going to process your request. And Knative comes with many useful features, such as automatic scaling. So it's going to figure out the number of pods you need to process incoming requests. So let's take a look at this example. So as you can see, we are getting many requests from the many clients. And Knative says, no problem. It's going to talk to the API server to create more pods. And the API server is going to talk to the kubelets on the workers. And kubelets are going to create pods. And once pods are ready, Knative is going to forward the request to the pods. And this is a configuration for the Knative. So let's focus on the line 1. The first line is API version. And we are using Knative API rather than the Kubernetes native API. And the kind is Knative service. And we specify the image associated with this Knative service. And we specify the port for this service. Oops. Okay, so this is great. Our machine learning service is serverless. We utilize Kubernetes resources. And we have to talk about important topic specific to machine learning service deployment, which is models. So machine learning service deployment is unique because it involves model binaries. So let's think about a simple example. Let's say one of the data scientists in your team developed a prediction model in scikit-learn. And you as a machine learning engineer are asked to deploy this model as a microservice. So the data scientist is going to send you this model binary in scikit-learn to you. I hope she uses SCP, not email. But you as a machine learning engineer receives this scikit-learn model and creates an image including this model binary. And you push the image to image repository. Kubernetes is going to pull the image from the image repository and schedule to run pods. So this is like okay as long as you're in a small team. But as you can see, we deal with 2 identical copies of the same model binary, which is not great. What if your team grows and you get more data scientists asking you to deploy their models, and each data scientist may use different machine learning framework, and each machine learning framework has its own dependency requirements. So, and you, as a machine learning engineer, you receive lots of model binaries, and you have to keep them in your environment. So it's going to be hard to keep track of the lineage of machine learning models once they're deployed. And the communication issue, it's going to be inevitably happen. And this happens. We don't know which model we are running. So how can we solve this issue? One way to solve this problem is to use model registry. I'm going to talk about Mlflow model registry as an example in this talk. But Mlflow model registry creates centralized model storage and for storing the model binaries. In this manner, data scientists can just push their model binaries into Mlflow model registry, and Mlflow stores lots of meta information about the models, and you as a machine learning engineer can view the information through Mlflow UI, and you can figure out the model name and model version for your service, and you can create and you can pass the Mlflow connection information to your image. Then you can create an image and push the image to image repository. And once the Kubernetes pulls the image, you can program your script to fetch model binaries from the Mlflow model registry. In this manner, you only deal with single model binaries, and that's a great deal. This is what the Mlflow UI looks like. As you can see, it contains lots of meta information, such as creation time of this model, last modified time, description, tags. Version is very important because we potentially develop lots of models. We're going to have multiple versions for the same model. And there's also a tag for the staging information. So maybe you as a machine learning engineer can say, okay, maybe I should use version 1 because it's tagged production. So it massively simplifies the machine learning service development process. And this is an example script to deal with Mlflow model registry. So left-hand side shows how to register your model in Mlflow model registry. First component is the training of your model. And once you train random forest model, you establish connection to the Mlflow model registry, and you log the model there. So maybe this is a script for the data scientist. And once the model is pushed and you are asked to deploy this model as a microservice, you can make the Flask app fetch the model when it gets started. You can pass the important information, model name version, Mlflow URI in environment variables. And first, it's going to establish the connection to the Mlflow model registry and loads the model from there and passes the model to the Flask app. And your app is ready to serve. So maybe the second script is for the machine learning engineers. Okay, so this is the final configuration file for our machine learning service. I promise you there is no more. So from line 1 to 11, it's identical. But sorry, line 1 to 14, yeah. But from line 14 to the end, I specify the environment variables. So this is how you can specify environment variables in Kubernetes. And also you can use secret. You can use a secret to store sensitive information within the Kubernetes space. And you can use the secret as an environment variable. So this is how you can do it. Okay, so before I go, I want to quickly talk about how I set up my Kubernetes cluster for this demo. So for this demo, I just used like vanilla native VMs offered by DigitalOcean, and I didn't use their Kubernetes product. I just used their vanilla VMs. And for my Kubernetes cluster, I used 3 nodes. 1 node is for the control plane, 2 nodes for the workers. For the workers, you only need 1 gigabyte of memory and 1 CPU. This is okay. But for the control plane, you need 2 gigabytes of memory and 1 CPU. Otherwise, you're not going to have a pleasant experience. And as long as you don't run crazy number of services, this configuration is enough for demo. And to set up my Kubernetes cluster, I used a Kubernetes distribution called K3s. K3s is a certified Kubernetes distribution that allows you to create a Kubernetes cluster that requires much less resources. If you wanna run vanilla Kubernetes cluster, this configuration is not gonna be enough. You're gonna need more computation powers. K3s is a lightweight Kubernetes, so this is gonna be enough for K3s. And the K3s comes with a single binary, so it massively simplifies the installation process. It's really, really easy to install. Vanilla Kubernetes, it's not very easy. Kubernetes is great because it's flexible. Kubernetes is bad because it's flexible. And on my K3s cluster, I run Knative. And for the image repository, I use Docker Hub. For the Mlflow model registry, I use 1 GB of memory and 1 CPU VM on DigitalOcean, and I run it outside of Kubernetes. And I run Mlflow server as a Docker container, and I use the SFTP server as the backend storage for this Mlflow storage. So thank you very much.
Yes. Yeah, we can get started with the question.
Yeah, thank you very much for your talk. It was very nice. I have a question in particular about the challenges you faced, because in the way you show it, Kubernetes are awesome, and it was very shiny and very clear. But I would like to know if you have faced any particular challenge with this workflow or some similar workflows that you have had in a more realistic scenario. That's my question.
So I think your question is about, like, is there any challenges I faced when I set up my Kubernetes cluster?
Yes.
That's a great question. First of all, it's hard to set up Kubernetes. So Kubernetes is a distributed systems. So it's vulnerable to like network issues. So sometimes it breaks. You want your nodes to be highly available. So if they're on the same rack, let's say in a data center, if the rack goes down, everything goes down. So maybe you want to use cloud providers, some VM for maybe some components like control plane. Yeah, okay. But that's a great question.
Thank you.
Could you just show the slide again where you had the link to your GitHub and
sure.
all that? Thanks.
Thank you for that.
So I have a question over here.
Yes.
Pertaining to when you were beginning to speak about Knative and how it was able to, like, as opposed to expending a lot of resources, monetary compute otherwise, it will listen for your API requests and then spin up pods accordingly. From a practicality perspective, like when the first request comes in, then wouldn't that take time to build from an image from the start? So wouldn't you just need to like at least have one persisting, like one pod existing in terms of like live production deployment?
Yeah, that's a great question. So the question is about, I think it's called warm start or cold start. So if there's no pod running, we have to create a pod. And so what about, the downtime? The answer is yes, and it depends on the size of your machine learning model. If the model is big, it takes lots of I/O connection, time. And I think it depends on your use case. You can configure Knative to run, at least one service, one pod. Yeah, so that's possible. And I think I forgot to mention, but the advantage of using Knative for serverless service is that so it's still Kubernetes, so it's going to be portable. So you can port your Kubernetes cluster between cloud providers. But yeah, thank you for the question.
Thank you.
Have you ever set this up in like a production configuration?
We we are using different Kubernetes distribution for the production. It's more suitable for production purposes. And I work in healthcare, so we have to set up on-prem Kubernetes cluster, because it's hard to migrate to the cloud for some regulation reasons. But yeah, I had lots of fun setting up the cluster, I would say.
Okay, yeah, yep. I mean, I work for a healthcare company too, and we use cloud managed Kubernetes.
Oh, that's great, yeah. Please talk to my manager. Yes.
Hey, so first of all, thanks for your informative session. You did talk about load balancer, right? So when you choose load balancer, is there a specific list of IPs you can cover, or they can talk about different subnets? How does you configure that up when you set up Kubernetes?
Are you talking about cluster IP or the
Cluster IPs, yeah.
Cluster IP? Yes,
Yeah.
yeah. You can set up a range. Even you can set up a IP range for the pods using the CIDR. Specific CIDR, CIDR.
CIDR, okay.
I forget that, what it stands for.
Okay, thank you. And can they talk with different subnets, or they can only work with one set of subnets?
So that's gonna be a difficult question. It depends on how you set up, subnet, because Kubernetes does not set up subnet, right? It uses existing subnet. So usually it creates an overlay network using UDP, connection, UDP tunnels. But there is a way to formulate Kubernetes cluster without UDP tunnel. It's called Calico. So it's gonna do IP in IP packeting, and you can talk to other subnets. Okay. But it's a kind of advanced topic, and it's for like DevOps, So, yeah, I love to talk about it, but yeah.
Thank you.
In your Mlflow setup, do you ever have a need to separate Mlflow models for different users or groups of users, or any kind of tenancy requirements? So you have one Mlflow, you just serve like one model or just one group of models?
Right, yeah, so that's a great question. The question is, like, you're talking about multi-tenancy, right, for the Mlflow. We don't have it. We love to have it, but I don't think Mlflow natively supports that. So.
I was wondering, if you had built something around that.
That would be a cool project. I mean, it's in my to-do list, but
Yeah.
Yeah, I think we have time for one last question.
Yes, what is the difference between Kubernetes as the distributions you've been using and versus Google Cloud, and how much easier is it, or harder, or what?
That's an interesting question. So Google Cloud is more broad. It covers more services. Google provides a Kubernetes service called GKE. So it's not an apple-to-apple comparison, in my opinion, but when it comes to other distributed systems, such as Mesos, Yarn, Docker Swarm, Kubernetes is known to be more stable, but it's more complicated. Thank you.
Yeah, apologies to the others who have questions. Yeah, and thanks a lot. Thank you, Kei, for the amazing session. Yeah.